Hello everyone, in this video we're going to look at an interesting example of the Coriolis force in action, and specifically we're going to imagine going to the top of a tall tower somewhere on the Earth and dropping a ball or some kind of particle and seeing where it lands on the ground. Now the obvious answer to this is, well, it should land directly below the point where you released it from, but we've got to remember the Earth is rotating about its axis, and that introduces a couple of weird effects called fictitious forces that we've got to take account of. And one of those fictitious forces is a Coriolis force, and it's going to cause the ball to deflect away from a purely vertical trajectory. So let's make a start on analyzing this situation and see how we can make sense of it. So I've got a couple of diagrams on the left. The top one is pretty simple. We've got a ball up there, and then we've got the ground as this horizontal line, right? And then separately, we've got this diagram of the Earth as a sphere seen from some distance. And we're going to define a coordinate system using this diagram at the bottom. Right, so let's say the center of the Earth is at this point in the middle, right? And we're going to draw a line from the center to the equator, which is this dashed line I've got on that diagram. And then we're standing at some arbitrary point on the surface of the Earth. Let's say maybe we're over there. I'm going to draw a line from the center of the Earth up to the point where we're actually standing. And the angle between those two radii that I've just drawn on, that is going to be denoted as lambda. That's called the latitude of the point where we are on the surface. Now, let's define some coordinate axes. We're going to first have a z-axis, which just points straight out from the center of the Earth along that radial line. So that axis there is our z-axis. We also are going to have a y-axis at 90 degrees to the z-axis, which basically points towards north, right? So it's kind of tangent to the surface of the Earth locally at that point. It's pointing towards north. That's our y-axis. And then to make this a 3D orthonormal basis, let's introduce an x-axis as well, which is going to be at 90 degrees to y and z. And therefore, it's pointing towards the east, right? So also note that the angular velocity vector of the Earth is basically pointing straight up like this. Okay, so that's the North Pole at the top. The Earth is rotating anti-clockwise around this axis, and so our angular velocity vector can be denoted, well, it's represented by this arrow, can be noted as omega like that. All right, so we've set up some coordinate axes. Let's think about the forces acting on the ball when we drop it from the top of our tower. Okay, so we have, firstly, a gravitational force, obviously. So let's denote that as Fg, right? Force of gravity. What's that going to be? Well, it's going to be mg. That's going to be its magnitude, right? If m is the mass of our ball, what direction is it in? Well, it's pointing towards the center of the Earth, right? By symmetry. And so it's going to be in the z direction, but it's going to be in the negative z direction because it's going downwards, right? Maybe it would also be useful to draw some coordinate arrows on this diagram at the top. Okay, so we've got our z-axis pointing up. We've got our x-axis pointing to the right, if that's east to the right. And then our y-axis would be pointing into the page from this perspective. Okay, so that's our gravitational force. Let's also think about the Coriolis force, right? So the expression for the Coriolis force, let's denote that as FCOR for short. The general expression is minus 2m omega crossed with v, where v is the velocity vector of the particle or the ball, right? And omega is the angular velocity of the Earth. And so let's evaluate that cross product and actually get this as a vector. So it's going to be minus 2m as a prefactor. Well, what is omega in terms of the x, y, and z basis vectors? Well, because it's purely vertical, it doesn't have any component in the x direction, right? Because the x direction is to the east. Okay, so the x component of omega is 0. And then we're basically splitting up a purely vertical vector, which is omega, into y and z components. And if you think about the geometry, all we have to do to get the component in the y direction, we have to take the magnitude of the omega vector and multiply it by the cosine of lambda. And to get the z component, we have to take the magnitude and multiply it by the sine of lambda. Right, so that's just from trigonometry, basically splitting up a vertical vector into two orthogonal components. And let's just write our v vector as three arbitrary components: vx, vy, and vz. Right, so representing both of these vectors as column vectors. And let's actually evaluate this cross product. So to evaluate cross products, I always use a determinant as follows. So 2m, we want to take the determinant of kind of a matrix, and the top row of our matrix is going to be x hat, y hat, and z hat, where those are the basis vectors of our coordinate system. Then the next row is going to be our omega vector, which is 0, and then omega cos lambda, and then omega sine lambda. And then our third row is just going to be vx, vy, vz. Okay, so if we take the determinant of that matrix, we're going to end up with a vector whose x component is going to be, right, vz times omega cos lambda minus vy times omega sine lambda, right? Then to get the y component, we want to do vx omega sine lambda, and then we'd be subtracting 0 because we've got 0 here multiplied by vz. And then to get the z component, we want to do 0 times vy minus vx omega cos lambda. All right, so there is our Coriolis force as a vector split up into components. So we've taken account of the Coriolis force. What about the centrifugal force, which is the other fictitious force that's relevant here? Well, the general expression for centrifugal force, let's write that out. So let's say F cent for short, is minus m omega crossed with omega crossed with the position vector of the particle or the ball, which is r. Now, if we wanted to solve this in full, we would get an expression for this and include that in our calculations. But to simplify things a bit, we're going to ignore it here. And the justification for that is that you've got two omegas. There's an omega there and an omega there. And so our final expression is going to be proportional to the magnitude of omega squared. Now, remembering that omega is the angular speed of the Earth isn't rotating around quickly, right? It's rotating around once every 24 hours. And so omega is actually a small number. That's why these effects are unnoticeable in our everyday lives, okay? And so because the centrifugal force is proportional to omega squared while the Coriolis force is just proportional to omega, we're going to neglect the centrifugal one because it's second order in that small quantity omega, right? So let's just write that down. It's second order in omega, and therefore we're going to neglect it for the purposes of this calculation. Right, so putting together the two forces that we are taking account of, gravity and the Coriolis effect, we can just divide them by the mass m to get an acceleration vector for our ball. Okay, so our acceleration vector, by adding together this fg and then this Coriolis force vector, dividing them by the mass, what are we going to get? Well, our x component will be, notice that there is a common factor of omega in both terms of our x component there. And so we can write that as 2 omega times vy sine lambda minus vz cos lambda, right? Remember, there's a minus sign in the front there as well. That's why these terms have kind of switched around. Right, then our y component is simply going to be minus 2 vx omega sine lambda, right, just from this term over there. And then our z component, remember we've got one contribution from the Coriolis force vector, but we also have a contribution from gravity, right, because that was purely in the z direction. So what's going to happen is that our z component of acceleration will be 2 Vx omega sine lambda minus the gravitational acceleration g. So there we go, that's our acceleration vector to first order in omega. Now, we're going to make another approximation, and in fact we should make another approximation for consistency. The idea here is that we've already said omega is small, so we're solving this problem to first order in omega. But if omega is small, then Vx and Vy, in other words, the y and x components of our velocity, are also going to be small, right? Because it's the rotation of the Earth that causes there to be x and y components of the velocity in the first place. And so if omega is small, then those quantities should also be small. And if we're working to first order in small quantities, then to be consistent, we should really consider the fact that Vx and Vy are small as well, right? So let's just make a note to summarize that. So we've got various quantities which we are considering small for the purposes of this problem, right? So the small quantities are, we've already said omega, but also Vx and Vy, all right? And so if we are working to first order in these various small quantities, well, we should neglect this entire y component of the acceleration, right? Because we've got Vx times omega, and that's a second order small quantity. We should neglect this Vx omega term on the in the z component of the acceleration, and we should also neglect the omega Vy term in the x component, right? And so making those approximations, we find that the acceleration is roughly equal to, so it's going to be just minus 2 omega Vz cos lambda. Then the y component will just be 0, and the the z component will just be minus g. All right, so that simplifies things a lot and allows us to make some progress on solving this. Notice that, or remember that the acceleration is just the time derivative of the velocity, right? So we can say that is roughly equal to the velocity vector with a dot on it to represent a time derivative. And so if we just integrate that, we're going to find our velocity vector. So how do we integrate this acceleration vector? Well, it's pretty easy to integrate the z component because we've just got a constant there. If we just integrate that with respect to time, we just get minus gt, right? And so the z component of the velocity is just going to be, let me just use normal equal signs. We can just remember that we've done an approximation. That z component of the velocity will just be minus gt, and there is no constant of integration, assuming that we drop it from rest, right? Because when t is 0, vz should also be 0. And of course, vy will also be 0, again, because 0 would just integrate to a constant term, but we've released it from rest, so the constant is itself 0. What about the x component of v? Well, the x component of v, we know the time derivative of that, vx dot, is this stuff up here, right? Minus 2 omega vz cos lambda. But now we know vz in terms of t. We know that was minus gt. So we could take that and substitute it into our expression in the acceleration vector. And what happens when you do that is you just get, well, the minus sign disappears, and you are going to get 2 omega gt cos lambda, right? And so fortunately, this is also pretty easy to integrate with respect to time. We just use the power rule, right? Increase the power of t by 1 and divide by 2. And so we find that Vx is equal to omega gt squared cos lambda. And again, the constant of integration is 0 because we've dropped it from rest. So if we know, well, now we know our velocity vector, we know all the components of the velocity, so we could integrate again to find the actual coordinates, right? So if we integrate this expression here, v for vx, again, we want to increase the power of t by 1. This time we're going to be dividing by 3. So x is going to be 1/3 omega gt cubed cos lambda. Again, if we place our coordinate system's origin directly below where the ball starts, then it starts at x equals 0, and so the constant of integration is going to be 0. So that's our x. And what about our z? Well, again, that's it's just a constant acceleration. And so if we know vz is minus gt, if we integrate that with respect to time, you get minus half gt squared. This time we do need a constant of integration, and the constant of integration is going to be the height from which you drop the ball, right? So if we say that we dropped it from a height where z equals h, then our general z coordinate is going to be h minus half gt squared. We could have just got that from the Suvat equations, right? Because the acceleration is constant. So there you go. Now we know x and z, and y is just always gonna stay as 0, right? So we can find the deflection, the amount of deflection at the moment when the ball hits the ground. The way to do that is first set z equal to 0, right? And so if z is 0, that means you've hit the ground again, because we put the origin of the coordinate system there on the ground. When z is 0, t is going to be the square root of 2h over g, right? Just rearranging that equation for z that we found previously. And then we can take that time and substitute it back into our x, right? Because that's going to give us the deflection in the x direction. And so let me just note that's the time when it reaches the ground. So what that means about our deflection is roughly 1/3, and let's put the t cubed in now. So t cubed is going to be the square root of, we just have to cube all of the individual terms under the square root, right? So we're going to get 8h cubed over g cubed, right? Then we've got our omega g cos lambda, right? So omega g cos lambda. We can simplify this a bit because g appears in 2 places. So remembering that this g here is the same thing as root g squared, we can put that inside the square root and cancel down a couple of powers of g, right? So what we can do is just turn the g under the square root into a g rather than a g cubed, and then remove the g outside. So that is just going to be omega. So there we go. There's an approximate expression for the deflection that we get, 1/3 square root of 8h cubed over g times omega cos lambda. So notice that this is always in the positive x direction. In other words, it's always pointing towards the east. So we can actually gain some insight into why the deflection is always towards the east with the aid of this diagram that's just appeared over on the right here. Now in this diagram, this curved line is just part of the surface of the Earth, and this rectangle is the tower that we're dropping the ball from the top of. And so this tower has a height of h, and let's say the Earth has a radius of capital R. Okay, now let's imagine looking at this system from the perspective of an inertial or non-rotating frame. And according to someone in that frame, this whole system is rotating towards the east with an angular speed of omega. And what that means is if you think about a point on the top of the tower, that point has some linear velocity towards the east at this instant, right? So this point at the top of the tower has an instantaneous linear velocity going over to the right like this. And to figure out what that velocity is, we just take the angular velocity omega and multiply it by the radius of the circular motion that that point is moving in. Now, the radius of the circular motion is going to be the radius of the Earth r plus the height of the tower h times cos lambda, and then we take that and multiply it by omega to get the linear speed. Now, the reason, by the way, that this cos lambda appears here is if you look back at this original diagram on the left and you look at this point where we're doing our experiment, that point is moving in a circle that looks something like what I'm drawing on now, looks like this, right? And so that radius is actually smaller than the radius of the Earth by a factor of cos lambda, right? Essentially, it's not moving along a great circle, it's moving along this slightly smaller circle. So anyway, if we go back to here, the point on the top of the tower is moving with this speed. What about a point on the bottom of the tower, in other words, at the surface of the Earth? Well, it's still moving to the right, but the linear velocity that the point at the bottom of the tower will have is going to be r cos lambda times omega, because the radius of its circular motion is just r cos lambda. And so the point on the top is moving towards the east more quickly than the point on the bottom. And when you drop the ball from the top, that ball will take on this eastwards component of the velocity, because the person who throws the ball is co-rotating with this with the tower, right? And so when you throw the ball or when you drop the ball downwards, it's actually moving to the east more quickly than a point on the ground is moving to the east, and that gives us a fairly simple and intuitive way of understanding why this deflection is always in the same direction.